So here we go. This is the plan. You should have picked up 3 pieces of paper. We introduce integration is what I want to do. I'm going to do questions on review 7, then talk about the test a little, then go review 8. If you haven't constructed your box yet, there's tape and ruler and scissors up there if you need them. I will probably just come around and look at that towards the end of the period, or if you want to bring it to me by the end of the day, that's fine. Ooh. Okay. So, how did that box go? That's about what. That's about what. Oh, that's like. You're right. It was 6 sides. That's cool. And the day or do where's my or do what? Okay, so I'll come around and check at that, or check it later. Also in terms of what's do, what's not do. Review 6, I wanted to have graded for you so you could have it to study from, but I just didn't get that done. Now, that said, if you feel like that would be of value to you, then come to me after class and just say, hey, can I get my review 6 back? And I'll just give it a quick look and check it out so you can study from it. Review 7 will probably be due today. We'll get through all the questions on review 7. The other class, review 8 was a humdinger. That was rough. Good thing you had 2 days. And believe it or not, it's normally 1 day, and I've actually cut it half. The first time I taught this, I put so much, I kept looking, like, oh, that's a good one, that's a good one. That review 8 was originally, took me 4 hours, and it was due the next day. And I had actually 4 students go to the counselor and ask to drop the class. So I cut it down a lot. I don't know what I was thinking. But at any rate, it was rough, to be sure. It was rough. I worked the key like crazy. I stayed after school until 5:30 and got the key done, then forgot to post it. So I posted it at lunch. It's there now, but we probably won't get through all the questions on review 8. We'll probably end up turning it in Friday. Also, this homework, review 9, I don't collect homework the day of a test. I have to grade the test, so I don't want homework to grade also. So review 9, that which you just picked up, that'll be due Friday. Everything clear? Okay. All right then. Let's talk integration, shall we? Really more antiderivatives than full integration. We'll do a few definite integrals, but this is blue. I would call this the integration chapter, technique chapter. We'll go through applications next week. So. Here we go. Now, this, I gleaned this from my review for the AP exam. So there are some on here that you haven't actually covered yet. That's would be covered later kind of stuff. This, although it seems like, gosh, there's a lot. There's 6, 12, 16. If you look at a typical calculus book in college, this at the back has a table of antiderivatives, or integrals, and there are 111. That's a lot. You still have to study stuff. Wow, that hurt. So at any rate, this is a subset of stuff you have learned and maybe a few that you have not yet learned. Do you remember the old power rule for integration? When you take a derivative, you bring down the power and reduce by 1. So when you take an antiderivative, you raise the power and divide by the new. Yes? Most people are fine with that. On 1 over x, don't forget the absolute value. Let's pause and talk about why are all these plus c's there, my friend? Constants could be unknown when we go back in time. When you go back in time, there's some gray area. Think of it like this. If you have y1 is x squared plus 1, and y2 is x squared plus 3. What do you know about y prime for 1 and 2? They're both 2x. So, that said, if you were to integrate 2x, you don't really know which of those was the original function. When you integrate, you're actually getting a family of possible answers all different by a possible constant that could have been there. You're getting a family of answers. How could you then find the plus c? If you had a point, if you had an initial condition. Okay? E to the x, that's the easiest antiderivative of all, just like derivative. Integrating a to the x, like 2 to the x, 3 to the x. We'll do that in a week or so. Make sure you have the signs right in sine and cosine. I think you probably worked out through those mistakes. Tangent, you could see it one of two ways. Either natural log of cosine in absolute value or natural log of secant. But both are found by use of. You remember that? Yeah, yes, if you think of tangent as sine over cosine, isn't that two terms, one the derivative of the other? So in this case, you let u equal cosine, in which case du is negative sine dx. So negative du is sine of x dx. It becomes negative 1 over u du. You integrate, that's negative natural log of the absolute value of u, and you sub back. Now then, how can those be the same? Negative natural log of cosine and natural log of secant. What the heck? How can those be the same? Why are those the same? I will wait. Okay, the log rules, yeah. You could put a negative 1 there as a log rule. You could bring it up to the exponent. Okay? Okay. So cotangents, similar. Secant and cosecant are a little more complicated. They're kind of funky. They require a real abstract kind of approach. We'll cover them later. They're fun. And then sine cubed, or to the fourth or something, those are also a bit of a pickle. They require identities, and we'll cover those later. Then these two, I definitely do want you to know, arcsine and arctangents inside derivative. Arcsecants, I don't feel is as important that you memorize that, but you should probably recognize arcsine and arctangent, at least until we get to trig stuff, in which case you won't need to have those memorized anymore. And then natural log is a big one that we'll cover later. All right, so that said, pause and try one. Try this guy, which asks you to make a verbal analytical connection. Try this one on your own or with your math amigos, and we'll talk about it in a minute. Just didn't record that well. I hope nobody missed that. Indefinite integrals slash antiderivatives is what we just did. Now let's talk definite integrals. The fundamental theorem of calculus actually is, geez Louise, huge. And I could talk about it for a month if I were so inclined. But we're going to just talk about it on its most basic level, which is to say the existence of the definite integral. What it means we'll talk about later, but for now, just know that when you get a definite integral, it's the antiderivative evaluated at the upper minus at the lower. Yeah? Okay. Try then this quick check to see if you know your fundamental theorem. Try that problem. It is not labeled in any way. My warning for you, especially as super smart people, is don't do too much mentally, okay? I imagine some of you can probably do the antiderivative and start plugging numbers in all at once, yeah? All right, on the AP exam, it's pretty well accepted that you will first show the antiderivative of x before putting in numbers. And 1 point for the antiderivative, 1 point for the evaluation. If you don't show the antiderivative first, if you just start spouting numbers, not only will you not get the antiderivative point, they also won't read it for the answer point. So you get 0 out of 2. You must show the antiderivative. Okay? What is, if you choose to rewrite it, it's x to the negative third. What's the antiderivative?
negative 2
x to the negative 2 over negative 2. Okay, you raise it and divide by the new. You can always check an antiderivative by taking a quick derivative. It's saying if I took the derivative, the negative 2's would go away, and I drop the exponent to negative 3, so I seem like I am doing this right. This then, whether you put the negative 1/2 out front and just focus on the x term, or you keep it inside, it doesn't matter. But when you evaluate, what did you get? However you chose to do this. 4 ninths?
Yeah.
D? Do we all agree? Okay, moving along. Techniques. Later on you'll learn trig sub and hyperbolic trig sub, which are super. You'll also learn partial fraction decomposition to cover non-repeatable, non-separable linear factors. Oh my goodness, that's a mouthful. Anyway, we'll cover partial fraction decomposition later. What you should right now is the U sub, the anti-chain rule. It undoes the chain rule. Yeah. It happens when you have one that's the derivative of the other. So, would you give that first one a go, please? Use U sub to choose the appropriate answer. If you're a little rusty, we will go over it in a minute. There's the answer. Boom. If the substitution u of 2 minus x is made, then what happens? Which one is equivalent? Let's pause here and actually talk about why this is so delightful. Why would you U sub that at all? Besides the fact that they tell you. In integrating now, why would you U sub? Does that look like a typical one is the derivative of the other kind of pattern? Not really. Now this is kind of a secondary use of U sub. U sub is also used for what I would consider a unfortunate sum problem. That's not mathematical at all, by the way. If you have this, how would you approach that? Actually, let me say this. How would you approach that? Separate it. Okay, you would separate it. 1 plus 1 over x dx, because a sum in the numerator could be separated like that, yeah? What if it had been the other way, though? X over x plus 1. Can that be separated? No. Now, you can get around that with a U sub. If you were to let u equal x plus 1, then the denominator becomes a u. And what does x in the numerator become? U minus 1. You've moved the sum to a place where you can split it and deal with it. So U sub also works in that sense. When you have a sum that's not quite right or in the right place, then you can get around that with the U sub. That's what they're asking you to do here. Give it a try, and we'll go over it in a minute. So, what are you seeing here? A, B, C, D, or E? I'm not seeing my answer at all. I don't know if that's the case for you.
D, you just have to mess with it a little bit.
D, you just have to mess with it a little bit. So I agree that, first of all, there's obviously doing some playing around with it because the limits of integration are not matching what I have. This is actually something I'm going to hit more on Friday, but rules for definite integrals. If I have a lower bound to an upper bound that's opposite of what I would normally expect, what can be done? You can switch the limits and make it negative. Now, if you switch the limits and make it negative, that negative would actually knock out that negative, and so I would be looking more like -1 to 1 of 2 minus u root u du, and that is E, yeah? Do you agree? E. Okay, how'd that go?
Wait, I have a question.
Yes, Sydney.
If you switch it so it's, because wasn't it first where it was 1 to -1?
It was 1 to -1, yes.
And then if you flip that to -1 to 1, don't you have to put like a negative sign outside?
You do. I took it and used it with the negative du that I'm getting at the end. And so
Oh.
that's where it went. I didn't show that separately. I apologize.
And then why was the du negative?
Because u is 2 minus x, if I take the derivative on that, people
okay.
want to say linear, so it's just dx, but there's a negative. Yeah.
Okay.
Okay. All right. So moving on to integration by parts, IBP, ultraviolet Ludo. I think you guys learned this at the end of last year. Honor students did. Maybe you practiced this to death. So let's review this really fast. I said that U sub comes from chain rule. Where does ultraviolet voodoo come from? It's undoing a derivative that came from a product. This comes from a product rule. This thing, besides being, hey, it's super duper, comes from the idea that if you took the derivative of two functions, remember U and V are functions, not variables. By product rule, the derivative would be u dv plus v du. Now, all that's great, but we're trying to develop a rule for integrals of products. If you integrated both sides, which seems like on the surface like it would be silly because you just took the derivative, why would you integrate it? But if I integrated both sides, then the left side, what's the antiderivative of the derivative? uv. Can I not split this up into two separate? Isn't that a rule of integrals that I can integrate the parts of a sum separately? Okay, now that's peachy. The idea is to develop a rule for an integral where the two functions are not related. So if you isolate this and move that over, then an integral of a function in some other derivative that's not related to u would be more like uv minus a new integral. And on the surface, it feels like you're making things more complicated because you're taking a problem that's just an integral and making it a problem with an integral and more. It seems like, why would you do that? Well, the idea is to exchange the integral you can't do for one that goes better later. So, with that said, the hardest part for students is sometimes choosing u. Now, I don't think Ms. Cannon taught it this way, so I'll be happy to go with what you have, but I was taught to choose u, you could use this acronym LIPIT. The best possible u is a log, or a natural log. The next best u is inverse trig. After that, polynomial would be a decent u. For example, any x to the first or x to any power. After that, exponential, like e to the x, which is actually a pretty terrible u. And the worst possible u is trig, because it doesn't ever go bye-bye. It just keeps coming back, sine, cosine, so on. All right, this is the worst u. Later on, when we get to circular integration by parts, or repeated integration by parts, tabular, you'll see those other ones. But let's get started here. Do you remember this enough to try it on your own or walk through it together? Try it on your own. Great. Try this one on your own, please. Ready? We're almost ready. What's your U choice? X. Therefore, dv is e to the x dx. Now, in order to plug in everything, I actually then need to, for each of those choices, find their companions. If u is x, then du is dx, and if dv is e to the x dx, then v is the antiderivative e to the x. With those four components, you have everything you need. Plugging in to the pattern, uv would be x e to the x minus v du is e to the x dx. Let's pause here for a second and talk the limits of integration. I have equality between that integral and that integral, and so I should have something about the limits in here. Whether you write them here and here, which is what I was taught to do, write them 0 to 2 and 0 to 2, or you could write them outside, way off to the side is fine. Or Miss Kenna might have had you do the antiderivative off to the side, bring it back, and evaluate it the limits. How did you guys do this?
We just did that.
We just did what I had there. Okay, super. All right, so after you've evaluated, you have a new integral, the theory being that it'll be an easier integral, which certainly this is. So integrating, I have x e to the x minus e to the x from 0 to 2. Filling this in, there's one last danger point, which is why I chose this. 2e squared minus e squared minus o when 0 goes in, that's nothing, right?
No.
No, common trap. People, when evaluating it as 0, will just say, oh, that's nothing. Is 0 in every function nothing?
No.
No, there are a lot of things where you put a 0 in and you get something. For example, here. When you put in 0, you get 0 minus e to the 0, which is something. Yeah, it's 1. So your final answer should be 1e squared plus 1. And it is
B.
B. Okay? How'd that go? Okay. That's all of the new. Bless you. So, done. Yay! Let's move on to review 7. If you have review 7, I think I had the key online. The only thing I didn't put online was the answers to this because I wanted there to be a fun math discussion around it. You guys probably had a little more luck with this because many of you asked good questions between the last few days and got started, especially with B, which is the hardest part. All right. Let's start with A. You've got this, and actually it's talking to fifth grade. There's a bit of a, Ms. Cannon did this differently on the justification than I do on part A, so we'll talk about that too. Okay, so A, write an expression for f prime. I hope that would be pretty straightforward. F prime is 3x squared minus 12x, yeah? All right. Now, it says use it to find the relative max and min values of f. So am I going to be getting x values or y values? It says use it to find the relative max values of f. That is a y value, okay? Not where the max occurs, what the max is. In terms of p, justify your conclusions. Now, I assume you set this equal to 0 to find the critical numbers. And you hopefully arrived at the critical numbers being 0 and 4, yeah? To get into the min-max question, did you do the second derivative test or the first derivative test? So much better. Why didn't you do the second derivative test? All right. Here we go. 0, 4. The signs went positive, negative, positive for the first derivative. Do you agree? All right then. At x equals 0, do I have a min or a max? A max. Give me a pre-calculus reason. Because a pre-calculus reason. Because a cube looks like that. And so the lesser point should be a max. And the rightmost point should be a min, right? Okay, now on the calculus level, which is what it takes to justify this, there's a max at 0 and a min at 4, yeah? All right, let's talk justification. This is where you and I might say this a little differently. F has a relative max, continue, at x equals 0. So when are you going to get the value in it?
Oh, just do the point. Oh, 0.
Okay, so I would say a relative max value of, what is the relative max value? P. Now, if you want to parenthetically say at x equals 0, hey, this is where it happens, fine, but make sure that the value is the star of the show. Okay, what is the maximum value of the function? It doesn't say at what point is the maximum occurring. It says what's the max value of the function. You should be giving me the max value of the function, p. Okay, at x equals 0, here's where you and I differ in terms of justification. Because, say your answer, please. That's not what the other class said. They said because the slope of f changes from positive to negative. Is that not what you guys said? Okay, now this we had a little fight about this. Maybe that sounded like Ms. Cannon said you've used it. I was told in last class, they said, well, you're given a function, so you use the function as your guide. The slope of f changes positive to negative, yeah? Okay, now, I understand that's a general rule of thumb good on the AP test, but my justification, my slant on this is that in no calculus textbook, and I have looked at probably a dozen, have I ever seen the slope of f test for extreme. Every textbook has the first derivative test for extreme. And to cite evidence, you use the first derivative. Okay, so in my mind, it should be, because, it sounds like you already said it right, because f prime changes from positive to negative. That's the theorem. I mean, it's an actual theorem. First derivative test. If the derivative changes from positive to negative, then max. That's the theorem in the book. Yes?
So on the AP test, which way do we do?
It would be accepted as to both, but I would prefer this. Okay? In some cases, that would get you. The slope thing would get you. What about a min? F has a relative min value of, we know it's occurring at 4. What is that function at 4? Hi, Kelly.
Bird's here too.
Where? Hi, Bert. I didn't even notice you. Hey, there's your brother.
How's that?
Okay. Are you just doing some calculus?
Yeah.
Okay, cool. Do you want, I don't have any extra homeworks for you to do, but,
Oh, okay.
okay. All right, F has a relative min value of, it's happening at 4. What's the F value at 4?
Negative 32 plus
Negative 32 plus P. 32 plus P. If you like, at x equal 4, that's kind of a cover your butt thing. Because F prime changes from negative to positive. Now this is obviously all the first derivative test. If you use the second derivative test, if you're the one person that did that and you want to see the justification, you can do it. Okay, doesn't look like it. B was the tough one. B was a humdinger, yeah? What did you say? B is between, sorry, P must be between
negative 0 and 30.
0 and 32, negative 16 and 16. Any others? I applaud you for getting an answer at the very least. It is 0 to 32. This was tough. This is great. You'll find that the AP test doesn't assess breadth of knowledge as much as depth of knowledge. Do you really understand calculus in your soul? Is what is amazing. Okay. So, we know that a cube, this is not all the work you would show for the problem. This is a learning one, all right? This is why I didn't put the key up. Cube shape could look like this, this, or this. Now, in all cases, a cube's derivative should be a square, correct? Think of the solutions to when that derivative is set equal to 0. When you have a quadratic equation, what kind of solution scenarios can you have? 2 real, okay? Which of these 3 graphs would correspond to 2 real derivative zeros? The last one, okay? What are other cases of the quadratic solutions? 1 real, okay? That happens when the quadratic formula has what here? When would this come out to be just 1 solution instead of 2? If this is 0. If that's 0, then plus or minus wouldn't matter, and it's 1 solution, okay? Which of the 3 cases would be 1 solution to the derivative? The second one, 1 flat spot. And then this case would correspond to a derivative solution set of imaginary solutions, all right? You with me? Which of the 3 cases are we working with? The third one, because we know that there are 2 real places where the derivative is 0. So it's got to look like that, yeah? So far, so good? All right, then. We know it's going to look like that. Let's consider, then, what that would look like on ye old axis. What if this curve, what if this curve is up here? How many real roots? 1. What if, now, it would be up there because the y-intercept is big. The p is so high that it's making it way up there, yeah? What if it's, and I should actually put it here because there's a 0 at 0 and 4, right? So it should be, that p should be right at the axis. Okay. What if the p is such that the curve is down here? Then how many roots? 1. What if the p is such that it's like, oh, baby. What? That's not, I just took it there. What am I doing? There. 2. Okay, 2. And that would actually be a double root. That would probably be a square or something like that. What about that? 3. All right. Now that's what we want. We want, they say, what does p have to be? So we have 3 roots. Now surely could be a sweet region in there that it's hitting 3 times instead of only 2 high and once or 2 low and once. So now the question is, all right, I kind of get the concept. How do we get into defining it? Well, let's look here. Think here. Where does this max need to be? All right, great. X equals 0. All right. Now, in terms of the y value, where's the y value of that point? Greater than 0. We have to have that peak above the axis so we get our 3 roots. When that point is below, we get 1 root. Yeah? So it needs to be x equals 0. I need the max above the x-axis. What does that imply then? F or f prime? Talk to me. F at 0 must be greater than 0. Now we're getting there. What's f at 0? P. P must be positive. All right? Now, let's talk this bad boy here. Where does the min need to be? Needs to be below the x-axis. At x equal 4, f needs to be below the x-axis. That implies that f at 4 must be less than 0. What is f at 4? We already found that, I think, in part A. Negative p plus 32 must be less than 0, so p must be
Negative 32 plus
negative
P minus 32.
p minus 32. P minus 32 must be less than 0, so p must be less than 32. If p is bounded on both sides, p has to be between 0 and 32. And then you would yield 3 real distinct, that means different roots. Okay? Okay, how'd that go? Wasn't that fun? It's pretty cool to think. See, I miss Bert. Bert is my all-time leader in moments. Have you ever had a class with Bert? Does he say that in every class, or is that just my class?
Every class.
I love that. I miss that, Bert. I really miss it. Thanks. All right. C. C is something else. Oh, C also was kind of funky. It's tough if you get 3 curveballs in a free response instead of just 1. Or 2 curveballs. 1 was pretty easy. This one had a little bit of a 2 curveballs. What did you say for P? In order to get an average rate of change of 1, P must be
Yeah, that's fine.
anything? You're telling me P could be anything?
Yes.
You're right. P can be anything. Okay? P can be anything. Now, again, understanding on 2 levels. I can make the symbols work. I can make that happen. The question is, can you get your mind around it too? So, the average rate of change. Wouldn't you say that the average rate of change is f at b minus f at a, 2 endpoints, slope between them, right? In this case, then, it would be f at 1 minus f at negative 1 over 1 minus negative 1. If you're like me, I just started doing stuff and saying, I don't know, we'll see, I guess. I just got into it. What's f at 1? Something like negative 5 plus p. Do you agree?
Yeah.
What's f at negative 1? Negative 7 plus p. Yeah? Over 2. That's the average rate of change. I actually just wrote that. So what does that come out to? 1. Well, okay, so now this is starting to kook me out. It says find all the values of p so that this equals 1. What if p is, looking back here where there were p values in there, what if p was 10? Would this come out to be 1? Yeah. What if p were 100? So it seems like if I find all the values of p, then it's all values of p. or all real numbers? Any real number. Now, talk to me about why that is. Why is the average rate of change between the points -1 on the curve always equal to 1?
It's constant, so it has no impact on the derivative, which is the slope. So that's
Yeah, if you think about the derivative, it's not even in there, and so the slopes would be the same. The only thing that it would affect is where it is, but wouldn't the rate of change between the 2 points be the same no matter where I put it vertically? So it's all good. It's all real. How'd you do that? Normally I would have a rubric and you could grade it out of 9. All AP calc problems are out of 9. But this, we're just learning here, so okay. Other questions on review 7 for the good of the order, maybe a 1 or 2 smaller questions. Yes?
3.124.
3.124.
That's like, great.
Sure. Let me find it. Where did I put it? 3.124. Which is, I guess, it would normally be box 5 if I had numbered them, but I didn't.
Yeah.
Okay. Okay. The function was h of t is t over t minus 2. The interval was 3 to 5. Okay. And so, if I recall, the question was find the absolute extrema of the function on the closed interval. Absolute extrema must be at a critical or an endpoint, so x equals 3 or 5, or a critical point. So, a critical number. So the endpoints I know easy enough. The critical points, I need to find where the derivative is 0. So, did you use product or quotient rule, I assume?
Yeah.
Low, d high minus high, below over the square of what's below. The derivative is t minus 2 minus t is just negative 2 over t minus t2 squared. In terms of critical numbers, what is the only critical number? T equals 2 is a critical number, but it is not in the domain. No, there's an answer. It just means it doesn't do anything funny from 3 to 5. It just moves continuously, monotonically. The derivative is always the same sign. So h at 3 is 3 over 1. H at 5 is 5 over 3. I said, by the extreme value theorem, the absolute max must be at an endpoint or a critical number. So the only two places I can look are those two. The absolute max is 3, h, which is h at 3. And the absolute min of the function is 5/3, which is h at 4. Okay? Any other questions on review 7? Yes? 16. Yeah. Okay. So I'm glad you asked. So first of all, if you looked ahead, that test review sheet at the bottom of the front says delta epsilon will not be 1. We will work towards mastery of delta epsilon, but it's not going to be on the test tomorrow. It's still worth a little bit of talking about, and you'll maybe not totally get it by the end of the time I'm done with this, but you'll be a little closer, and that's all I ask. So, number 16 is in part A. I think this is right. Do I have that term? Yes. Okay, prove that by finding delta such that if x minus 2 is within delta, as a consequence, it'll follow that f minus L will be less than, I make it 100 for the first time, yeah? Okay. Okay. Let me write here this theorem. This is the definition of a limit. A limit or actually, the limit as x approaches some number of a function can be said to be what you say it is, only if there is a delta that can be found, which is a closeness to x, such that if x is within that delta of what you're approaching, it'll follow that f will be within some arbitrary closeness to the limit.
Like, so that symbol is arbitrary limit.
Epsilon is some arbitrary number. Sometimes that case will be given, and sometimes it'll like a number, and sometimes it'll just be left epsilon. Graphically, it might help to take a look at this. Say f of x looks like this. And you want to know as x gets closer and closer to some actual number that's the question, what is the limit approach? Now the y value is the limit, yeah? All right. Although we use direct substitution all the time, that's actually a violation of the idea of the limit, because the idea of the limit is what it approaches, not necessarily what it is. So that's why this rigorous idea. The part that they will ask about is they'll say, okay, I believe that the limit is L if you can get me a function result that's within this close of the limit. Now this gap here, that gap, or how close I need to get to the limit, that's epsilon. It could be on either side. You might need to get me within epsilon above or below, or both, yeah? So, again, that's epsilon on either side. Your job is to say, well, can I find, in order to get that close, how close would I have to get x to c? So that as long as I'm within this close, I'll end up within that close. This closeness to x, that closeness to x, that's delta. That's what you're looking for. You're trying to say, if you're within a billionth of 3, the limit will be what it is, okay? Are you with me so far? Now, this really consists of 2 parts. Every one of these consists of 2 parts. Find the delta, and that's by working backwards from f minus L towards x minus c. This is actually rough draft / scratch paper work. Usually, once we get to formal definitions, delta epsilon, you won't even do that anymore. You're just going to do it off to the side to find it. The actual proof, think about like the research of your paper, all right? You don't show all those documents and all those things you took. The final paper, the proof, is the going forward. You identify the delta that's going to make your proof go, and then you show that if x minus c is within that delta, then it'll follow or can be taken to the difference between the function and the limit will be less than epsilon. That's the process. And again, we're going to go through this quite a bit more thoroughly in set 103. But that's the plan. Are you with me so far? All right. Again, I'm just shooting for a decent understanding of what I'm talking about here. We'll get to the better soon. So on part A, the idea was to show that if when does x goes to, was it 5 or 2? 2, 7. When x minus 2 is less than some delta, then I'm just rewriting this again. Less than. All right. The first thing, like I said, then we need to find the delta. If I want to get within 100th either side, what does that mean? I have to get close enough to x. So finding the delta, if I start with the fact that f minus L needs to be less than 100th, the function is x plus 5, the limit is 7, and so that has to be the case, yeah? You with me? Okay. Absolute value of x minus 2 then must be less than 100. Now that's to say if I want the y to be within 100, then the x has to be within 100. Why is that the case here? Why are they exactly the same? Look at the original function. It's linear with the slope of 1. Okay, that's why there's this perfect y-x relationship here. That's why they're the same. Now, if this line had been steeper, then to get within this size gap here, that would actually cause a little closer to x. So the steepness, the slope will come into play. But because this slope is 1, that's why we're getting a straight up delta can be just like epsilon. Whatever you want epsilon to be, delta can be the same. All right? That implies then that the delta, once you get this isolated, you know your delta. You know x has to be within a hundredth of 2. Now the actual proof. Whether you showed that or not is up to you, but in terms of the proof, thank you. Here it is, right? Yeah. All right. The actual proof, it goes something like this. Identify your delta. If you let a delta equal 0.01, it will follow then that if x minus 2, if x is within that proximity to 2, it'll follow that the function will be within epsilon, or actually 100th of the limit. Now this is then where you pretty much, if you think about this, it's really just reversing the process. And this is the part that makes students mad. It seems like didn't they just do that and they're just writing in reverse? The answer is yes, but remember in your final work, it won't actually show the backwards and the forwards. The backwards you're going to leave off, and it's just the forward proof. And it really looks like you're a genius. You're just coming up with this, hey, here's the delta. See how it works. And it'll look really cool when it's, especially when it's a curve, all right? So that said, this is a nice little guide to see what to do. I need to show that if this is the starting place, that this will follow. So if x minus 2 is less than 100, how do I get from there to f minus f? Look back at your previous work and turn it around. There, see? So that means x plus 5 minus 7. Did I break any rules of math? No, I think anybody will agree that negative 2 is the same as 5 minus 7. Okay? Furthermore, by definition, they told me that x plus 5 is the function, and 7 was the limit, and therefore it must be the case that the function is within 100th of the limit. You see where I'm coming from? Okay, now for b, instead of a numerical delta, you're just going a numerical epsilon, they're giving you an unknown epsilon. That means then that delta won't be a number like it was there. Delta, how close I need to get x would be dependent on how close I need to get y. And so delta will be a function of epsilon. Okay? Delta will relate to the epsilon asking. We know that it's a one-to-one correlation. So we know that here, for the proof to work, we could say let delta equal epsilon. Oops, epsilon, that points your way. Epsilon. I will show that if x minus 2 is within delta away, it'll follow that the function and the limit will be within whatever epsilon, the desired closeness of the function. Well, if x minus 2 is less than epsilon as my starting point, delta, and delta is epsilon, then x minus 2, instead of being less than delta, I could say it must also be less than epsilon. Again, I want to show that it follows that this is going to happen. So now what do I do? x plus 5, x minus 7. That's mathematically true. And we replace f of x minus L must be less than epsilon. That satisfied the definition of O. Again, if you're iffy with me, then I'll take it. Bigger fish to fry. We'll come back to it and master it later. Other questions on review 7? What time do we get out of here? Oh, we're doing it. What period?
6.
Oh, perfect. Okay. Are we good on review 7? Yes, ma'am. Oh, sorry. Just a second. Yes.
15.
15. What did you say, 13?
13.
13. 13. H9. I did this in the last class too. I can't remember where. Somebody have their packet in front of them. Sorry.
Yeah.
15, H9. Let's see. Oh, yeah. Okay. Y equals x squared plus natural log of x. This actually, I'm glad you asked this because I forgot to put this on the review materials, but tangent line, normal line definitely is possible calculator, or sorry, test question. It says calculator required, which is to say never. You should never use a calculator for this. It should not be necessary. To get a normal line, it's a lot like a tangent line process with one small twist. Do you still need a point to get a normal line? Okay, what's the point x and y? 1 and? I agree, 1. Okay, sounds good. The point of tangency and the point of normalcy, they're both the same. Those little, I think, vectors when I do these, but they both are at that same point. The slope will be a little different. Let's start with the tangent slope. The tangent slope is the derivative, yeah? What's the derivative? 2x plus 1 over x. At 1, then this is 2 plus 1 or 3. What I just did there is terrible work. Why is it terrible work?
So you didn't show.
You're saying y prime everywhere is straight.
Yeah, I bled in from general derivative into specific numerical derivative. That's bad math, and it'll definitely cost you in the AP test. Isn't this the general derivative? Is it always equal to 3? No, okay, so either say this in separate steps, this is y prime at x, and this is y prime at 1, or say, hey, I'm about to do this at 1, something to differentiate between the two, right? At any rate, that 3 is the tangent slope of the curve. Normal slope is perpendicular. So what's the normal slope? Negative 1/3. After that, write the tangent line is normal. Y minus, or the normal line in the same way. Y minus 1 is negative 1/3. X minus 1. I don't care what form it is in the answer packet. If you left it as point slope form, I'm fine with that for sure. Right? That make sense? Okay. And then I think, what was the other one? 13? Is that right? Okay, 13. H3. Can I just get back to the question? Oh, freaking me out. I thought she just got up and walked out of my class. Crazy. Thank you, sir. 3.
Right here.
A little late to okay. Okay, so you definitely should have down cold your definitions of the derivative. We'll talk the test in a second. The idea, though, is use the alternate definition to find f prime at 2. They were kind enough to give it to you. I most certainly would not. But do have deep into your brain the 3 definitions of the derivative. As applied to this problem, the limit as x goes to a is going to be the limit as x goes to 2. F of x is x squared. F at a is f at 2, which is 4. And x minus a is x minus 2. That most certainly, as all derivatives are, will come out 0 over 0. The idea of a derivative being infinitesimally small change in y over n, that's the whole idea of the derivative. Getting the points close together. They're going to approach 0 over 0. Whose is this? Oh, thanks. Okay. So that'll always be the case. In this case, the idea is not that you say, all right, screw this, I'm going to go back and use the power rule. The idea is that you do the algebra to show how it comes out. So, what algebra can be done?
Minus 2.
Yeah, you deal with the whole. It's kind of funny, but every derivative really represents a graph with a hole in it. And when you remove the hole, there you go. Okay? All right. Looking through the test, I'm not big on test prep, but it's definitely fair on your side to say you should at least tell me what the test is over, right? I mean, that's fair enough. That's not too much to ask, is it? So this is the huge stuff of the test. This is kind of how I start my test. I think, all right, what do I want to hit? I put the skeleton together, and then I try and figure out good problems to measure that which is being covered. In terms of the pre-calculus idea, seems like most of you are good on trig facts. Trig graphing, quite frankly, I absolutely deplore most of your trig graphs, but I don't want to grade them, so I'll figure something out there. It might just be, can you tell me the period appropriately, or the first positive max appropriately? Could you do that? I hope so. Whether you can construct a graph with a consistent scale, I would say that's a big no. That's a no. Parent graphs, we talked a lot on review 1 or review 2 about parent graphs and how they're shifted around, transformations of graphs. You should be good there. For the most part, you are. Domain, what are the 3 restrictions on domain? Give me one thing that breaks math. Negative and a root. Give me another. 0 in the denominator. And then the one that nobody can ever come up with? That's 0 in the denominator. Log of 0 or negative. Okay, those are the 3 restrictions on domain. Everything else boils down to that. Tangent, for example, really amounts to 0 in the denominator. So, those are the 3 restrictions on domain. Be able to deal with them. Intermediate value theorem, I'm very pleased with how well you do intermediate value theorem in an AP style. I want to also ensure that you can do intermediate value theorem problems that aren't slap you in the face, use the intermediate value theorem a little more subtle. I didn't put one of these on the back, but we did a problem like this where why must there be a solution to this kind of thing? Why must it have at least one solution? How would you go about that? And again, I'm not going to say use the intermediate value theorem to solve this problem. You need to know. How would you go about it? Show it must be less. So what's less than 0? Negative. Show it's got to be negative somewhere. Then show it's got to be positive. And there claim the intermediate value theorem applies because it's continuous. Okay. I wouldn't expect you to actually find a numerical value at negative 10. You just put negative 10 in and say this will be negative. Okay. Wouldn't you agree that that would be negative because that's the least it could be is 1, negative 10. Remember? We talked about it. Yeah? Okay. On limits. One-sided limits, you're fine. Remember, there are actually 2 cases we talked about where a limit D and E. By the way, those asterisks mean times, places you might study. I'm not big on studying for math, but sometimes there's a few little facts you need to have down. What are the 2 cases where a limit D and E? Oscillation. Beautiful. You remember that. That's great. Oscillation, and the more common, one-sided limits not equal. Yeah? Yes, in that case you can say oscillation because, yes, that's true. The D and E, because the one-sided limits not equal, you need to have evidence. You need to show the one-sided limits and then say, see, they're not equal. The 2 famous limits. What are the 2 famous limits? Sine of x over x as x goes to 0. What is that? 1. The other is, as x goes to 0, cosine minus 1 over x is 0. You should be able to work with limits graphically, analytically, and numerically, including making a table. Sandwich theorem, it'll be pretty clean. It wouldn't be too funky where you had to actually come up with the maximum and minimum functions. And then connection to vertical and horizontal asymptotes. Can you connect limits to vertical and horizontal asymptotes? In other words, if I said, find where this has a vertical asymptote and justify your conclusion with a limit, would you do that? Okay, there's a problem on the back where you might try that. You need to make the connection that the limit as x goes to c, if that function turns out to be infinity, then that implies a vertical asymptote. And as x goes to infinity, equaling a constant implies there's a, and that's plus or minus infinity. Okay. All right. That's the connection. Continuity, you must know down cold the definition of continuity, which is to say the limit exists, the point exists, and they're equal. The limit only exists if the left hand, right hand are the same. Okay. Justify continuity or discontinuity, and know the three types of discontinuity. What are the three types of discontinuity? Vocabulary wise. Jump, removable, infinite. Okay. Derivatives, you should know the three definitions of the derivative. The first definition, I suppose, you could actually break into two subcategories at a point or at any x. But you should be able to work with that on two levels. You should be able to find a derivative using the definition, or you should be able to recognize the limit as, oh, that's the derivative. Let me just go over here and use the power rule. You know what I mean? You know what I mean? Do you need an example? Okay. Estimate derivative from a table. Make sure you use the average rate of change to estimate. Make sure you're intentional about an estimate. Make sure you show the points you're using, and make sure you pull points as close as possible. If it's a case where you could either go one-sided or symmetric, then I would take both if I didn't have a multiple choice. All right? Differentiability. What are the three reasons why a function is not differentiable? Not continuous, a discontinuity, sharp turn, vertical tangent. Okay, notice he said vertical tangent, not vertical asymptote. Why not vertical asymptote? That's discontinuity. We already have vertical tangent, right? You also need to be able to prove derivative doesn't exist using the definition. That was on review 6, I believe. If you need to see that, or you want to go over that, come in and you can. By the way, I will be here 7th hour. I'll be here after school. I'll be here before school tomorrow if you want to review. You should be able to take the derivative using all the rules. Most people are killing at that. That's great. Implicit derivatives. When you get an implicit derivative and you have your dy dx, how do you know when you're getting a vertical tangent? Think rise over run. When would it be vertical? When there is rise, or is there not rise? When there is rise but no run, that's vertical tangent. When would you have a horizontal tangent? When there's no run, but there is, or no rise, but there is a run. Yeah? So non-zero to zero and vice versa. Okay. The related rates, it always kooks me out. The related rates comes in the applications, or sorry, the derivative technique chapter, but it always does, not applications. Doesn't it seem like it's an application derivative? Whatever. So that could be on there, and that's it. The back is good free response kind of practice on these ideas in a rigorous, these are hard kind of, if you can do these, you're in good shapey kind of way. The test will be this and easy, not this and hard. Okay. That said, that backside is just practice. It's do it if you want, ignore it if you want, make a paper airplane if you want. So it's up to you. I will work a key. I'll post it on my website. I will be here before school if you want to talk about any of those questions. Those are a pretty good review. That's it. Okay? Any questions? Cool. How you feeling? You'll be fine. Okay, you'll be, just show up and be yourself. Be your normal, brilliant self. Hi? Okay. You guys kind of stress me out with your stressing of yourselves out. I wish you'd lighten up a little. That's all. Boom. Review 8, homework 8. Oh, wasn't that a humdinger? That was a humdinger, right? Okay, let's have review 8. Unfortunately, I just posted these, so you might not have had a chance to look at it. So, some of these I feel like I definitely will want to talk about. And if I don't talk about it, if one I thought was an easy one, you just have trouble with it, we'll go back over the base. Let me go through a few of the toughies, shall we? On number 1, A, check your answer. What did you say for A? Once. Anybody else?
I said at least one.
Okay. At least. Yeah. You must have at least. At least is important. Don't read too much into a table. Don't say, well, it's got to happen once. You don't know. It must happen at least once. All right. B is the harder part. At least once is A. B. F at 4 must be between, most people probably got the lower limit. It must be greater than 19. The harder one was the upper limit. 22 is close. It's 23. Must be less than 23.
Oh, I said 22, please.
You have the right idea. Do we now talk about the 23? Or no, you got it? Talk about it. Okay. It goes like this. 1, 2, 3, 4. Now, if you just said x greater than 19, f greater than 19, I understand where you're coming from, and you're on the right track, but there is an upper bound on this. And the upper, first of all, are we clear on why 19 is there?
Yes.
Okay, that most people will find that, yeah, because the derivative is positive. All right, this part, why not just as big as it wants to be? Well, it really goes to the second derivative. Consider the second derivative. Now, the second derivative is the change in the first derivative, which is to say, second derivative is the change in the change. What's the change here? 5. What's the change here? 4. Now, the second derivative has to be consistently going the same way. What's the change in the change? The changes are decreasing. The changes are decreasing. If I were to analyze the change in the changes are decreasing. So the next change must be less than, if the previous change was 4, then the next change must be less than 4. And if the next change must be less than 4, then that next point must be less than 23. Okay? Now it would be tempting to say, I can see why you'd say 22 because 5, 4, 3, but really couldn't it be anything less than 4, like 3.9? So really, that's why 23. Okay. Does that make sense? Box 2. Box 2. After doing this, I redid this for next year because box 2, it was supposed to get you using the second derivative test. But what did you find on the second derivative test? It failed. The second derivative at the critical number, which was 0, is undefined. So the second derivative test fails. That stinks. I wanted to get to one where you actually had a second derivative test work. So what happens if the second derivative test fails? You use the first derivative test, and what did you see there? Min or max? Min at 0 to 3. Okay? Because the first derivative changes negative to positive. Okay. 3. Again, stinker. The first derivative was 0 at x equal 3 pi over 2 and 7 pi over 2, yeah? Unfortunately, the second derivative at those points, again, was, or not again, this time the second derivative at those points was 0. And that, again, the whole idea is at the flat spot, is the curve concave up or concave down? It's got to have a sign for it to all work. If the second derivative doesn't have a sign, then the whole second derivative test fails. And so, again, the second derivative test fails, and you had to go back. But when you go to do the first derivative, it might have looked something like this: negative, 0, negative, 0, negative. Where are the extrema? There are no extrema. If you were to look at this curve, the y equals x is linear, and the trig causes it to go flat a while, but then, so it never actually has extreme. Okay, questions? All right, box 6, which is actually box 4. I took a couple out the homework and forgot to renumber the boxes. This one, my advice to you would be to factor and clean up as you go. If you don't factor and clean up as you go, everything starts to get out of control ugly. So, although you might have had the right answer here, my hope is that you didn't just make your life miserable along the way. Do you want to walk through how to do this really cleanly, or no, you think you're good?
Yeah.
Okay. So, again, this is just towards getting you to make your life easier. Not necessarily get you a different answer, just make your life a little easier. So, pay attention to how I clean things up as we go, and you'll see this go much better. I know this is an x to the 4th, which could look like a lot of different shapes, but let's proceed. I did not multiply it out. That probably doesn't help you, because if I did, it would be x to the 4th. When I took the derivative, I get a cube. I have to solve synthetic division cubes for the solutions. I don't want to do that, all right? So I'm going to leave it factored out. The product rule is first derivative of the second plus second derivative of the first. Greatest common factor. What is it? Take out x minus 4. How many? 2 of them. Leaving you with a 3x here and an x minus 4 there. So the cleanest possible second derivative, in my mind anyway, is x minus 4 squared times 4x minus 4. The second derivative is 0 at x equal 1 and 4, yeah? Now it's tempting to then make the sign chart there. I recommend you hold off. Okay? We're gonna, when you read ahead and it says go first and second derivative, it's better, easier to do what I consider a super chart back in my day. This, by the way, this is my strongest. I didn't have a graphic calculator. We did hundreds of these, hundreds. Okay, so moving on to the second derivative. Look at this first derivative. That's the place we're going to take our derivative on. First stays the same. Derivative of the second plus second stays the same. Derivative of the first. And again, do a little bit of cleanup. Greatest common factor. Greatest common factor. X minus 4. Now, this one still has an x minus 4 and a 4, so what's left would be 4x minus 16. Do you agree? Mm-hmm. Okay. This one had an x minus 4 removed, so what's left of it is 8x minus 8. The second derivative then is x minus 4 times 12x minus 24. Therefore, the second derivative is 0 at 2 and 4. All right. Now, in terms of behavior, I'm going to make a chart, both of first and second derivative, so I can each region say increasing concave up, decreasing concave down. Okay? I can get little bits of information that are very complete. So considering both sets of interesting numbers, my first interval would be negative infinity to 1. The next interval, actually after 1 then, the interval would be from 1 to 2. Then I look at 2, and then from 2 to 4, I look at 4, and then 4 to infinity. All right? Now, at each of those places, I'm going to look at the first and the second derivative. The first derivative, here's where I'm going to look. If I put in a negative 1, the square is always positive. This would be negative. So positive, negative is negative. At 1, I have a 0. At 1.5, this is still positive, but now this is going to be positive, so positive. At 2, do you agree that 2 doesn't really have any impact on the first derivative? That's a second derivative number, so it's going to stay positive and positive until I get to 4, where it's 0, and then at 5, I'd be positive, positive, and that's positive. Okay, cool. Second derivative, here's where I'm going to look. The factored form is the best place to see its signs. At negative 10 or whatnot, negative, negative, which is positive. Notice again, the second derivative doesn't really have anything to do with 1, so it's going to stay positive there until I get to 2. And when it's 2, the derivative, second derivative goes 0. At 3, I'd then be negative positive, which is negative. At 4 is 0, and at 4, after 4 is positive. Now let's graph. I don't really need a ton of points, but if you can get at least a point or two to kind of anchor the graph, do that. Look at the factored form of the original function. What are 2 zeros? 0 and 4. All right, those are the only real points I'm going to find accurately. The rest are too much work. From negative infinity to 1, describe the graph. Decreasing concave up. At 1, what happens? If the derivative is 0, there's a horizontal tangent. Okay? From 1 to 2, describe the graph. Increasing concave up. At 2, the second derivative is 0, which might be inflection, but you need to look on either side. Do you have inflection at x equal 2? Yes, all right. Now that's going to bear out in a second. From 2 to 4, describe the graph. Increasing concave down until I get to 4. And then at 4, increasing concave up. There are inflection points twice, at 2 and 4, where it goes from up to down and down to up. And that's a good graph. Truth be told, f of 1 is actually pretty low. But that's pretty good. Okay? With me? That's called curve sketching. Back in the day, it used to be a really big part of California. Where did I leave off? Box 7, most people are pretty good at that kind of FF prime F double relationships. Are you cool with box 7? If so, hang on to it. Ask me later. 8. 8, you don't have an answer to, so my answer to 8 was the velocity is 10 root 11 miles per hour, which is about 30-something. 30-something, 33 miles per hour, something like that. Okay? Pause real quick and plug for math here. Gosh, if you read this question carefully, it's like, what velocity of traffic maximizes flow? This is actually an applied math, very famous applied mathematics question. And if I were in your shoes, and you're going to see driverless cars like crazy in the next 20 years, there are going to be applied mathematicians working all over the place to decide how to make those cars. Now, if you're a mathy person but not a sciencey person, which is what I was, man, you should consider applied mathematics because it's an awesome field to go into. Consider it. It's super cool. That kind of question you would do. And I can talk to you more about that. I'm a member of the Society of Applied Mathematics thing. There's also a really cool competition that Cooper Dale and Kenny Lou did last year. It's just awesome. It's really cool. So, yeah.
I was part of that.
Were you on that team?
Yeah.
Your write-up was fantastic. It was so cool. Was it? Did you guys
Yeah.
enjoy doing that problem?
Yeah, it was really fun.
The level of that, really, that's like junior level undergrad, that problem. It's so crazy. You guys were awesome. You killed it. If you want to see their paper also, I can show you that. But man, I don't really know you very well. But if Cooper Dale or Kenny Lou came to me and said, write a letter of recommendation, I could write for 3 weeks. It's crazy. It's awesome. Anyway, applied mathematics. Yay, that's my point. Back to the lesson at hand. Number 10, conceptually not hard, but the devil's in the details. Were you able to make it work without making error? That's the question. 10. You're fine? You got through it, or no, guide me, give me a little start.
Can you just tell me the answers?
I can tell you the answers. Those answers, oh yeah. Doggone it, you guys don't even have the answers. Sorry, the other people, this was an odd, so they had the answers in the back of the book. The x, which I did not ever pick up my calculator. The x was 32 over 4 plus pi, which I would imagine is about 4-ish. And the y was 16 over 4 plus pi, and I would imagine that's 2-ish. How did you do that?
Sketchily.
Huh?
Sketchily.
Sketchily? Is there a word?
Very sketchily.
Shall we get you started, or no, you're fine, move along?
Started.
All right, so looking... Bro? Was that bro to me? Did somebody just call me bro?
No.
Okay.
Bro.
I'm not that kind of teacher. We're not friends. I know some teachers, that's their main goal in life is to be a friend. I don't need, you're not my friend. Sorry, I have friends. Do you have friends? Let's just keep it that way. At any rate, the area of this to be maximized is xy plus a half circle. The radius being x over 2 quantity squared. So my cleanest possible area equation was xy plus pi over 8x squared. That pi over 8 thing actually happens a lot in problems we're going to do later, cross sections with. Oh, it's so cool. All right, but that's your area equation in a clean form. The perimeter was 2 y's, an x, and a semicircle's perimeter. If a whole circle is pi d, what's the perimeter of a semicircle? Pi r. And pi r is pi x over 2. Okay. Now we know that needs to be 16. The next idea is that we want to get the area equation down to 2 variables via substitution. So we're going to solve this from y, and it'd be something like 16 minus x minus pi over 2x minus, and then divided by 2, which makes y's cleanest form 8 minus 1/2 x minus pi over 4x, yeah? Stop me if you disagree. The hardest part of this is if you have done it, trying to find where you went wrong. That's a toughie. If you need me to do that, I'm pretty good at that. Y, 8 minus 1/2 x minus pi over 4x plus pi over 8x squared. Rather than to do the derivative on that, I did choose to clean it up. So when I cleaned it up, I have 8x minus 1/2 x squared minus pi over 4x squared plus pi over 8x squared. Final version, 8x plus negative 1/2 minus pi over 8 x squares. If you had trouble, you might go with that as your area equation because that derivative goes pretty well. A prime is 8 plus negative 1/2 minus pi over 8 times 2x. That then should get you right. Okay? What time are we doing here? We're almost out of here. So I guess we're not going to get through those, which I didn't. I will, my key's actually there now, so if you want to look at the key, just so we're clear, to remind you, I want homework 7 today. Let's start with 6. If you want 6 back to study, come see me and I'll quick grade it and give it back. 7 is due today. 8 is not due today, it's due Friday. 9 is your homework tonight, but I don't collect homework on test day, it's due Friday. Nothing's due tomorrow. Be ready for the test. If you want to do the review, it's up to you. I will work the key and put it online, and I will be here 7th grade, after school, and before school tomorrow if you want to talk about anything leading into the test. No. Have a nice day.
Do you need our boxes?
If you finished your boxes, I looked at the boxes that were out on the desk. So I have Carla, Lauren, Alyssa, James, and Angie. Those boxes I've seen. If I didn't see a box, then make sure I see it by the end of the day.
Can we just like throw it away now?
I'm just gonna.
Oh wait, we have to not over it.
No, it's as long as you have to work on the paper, it's fine. I don't need to see the box.
Oh.
Oh, the worst one.
So yes.
Oh, you did all your work on the box? That's cool. That's what I did too. That's kind of fun. Box, who's showing me?
I was going to.
Oh, okay, go for it.
I finally
Can I
figured
like set 6?
Yes. Thank you. Okay. Cool. Very good. Now put your jewelry. Okay. Let's see. Actually, I
No,
got
it's yeah. Like it was
Is that it? I said no. That's on soup? Oh. I'll figure it who else can say homework?
You're so funny.
Who else needs their homework? So sorry.
Oh, I did. Oh, wait.
Okay. Alright.
You know what? Maybe I'm a
The rest to be given
Okay, I think we should adjust this. So instead, we're 7.
Oh, when you make your box, you're going to cut out 4 corners, right?
Okay, what can I do first?
So all the seniors have to go to counseling today during 7th hour to this area finished the box.
Good point. I'll
Okay, thank you.
If we even know like we got it wrong, like the dimensions like are wrong.
I'm not getting on accuracy. It is pretty easy to check, though I can see the box. Yeah. Do what
And
you.
if we
It's up to you whether you fix the box and redo it, or if you just go with your measurements. That's up to you. As long as you do it.
Can I ask you a question?
Sure.
So, So you know, like the maximum amount of volume that you can have in a tube, right?
No,
Oh shoot!
not necessarily. If the paper were square, then the max would be.
Right.
This is not
So is this like a blank start then? Like
No, that's what they'll do.
I try to dry on like a little here, but I wasn't sure.
Oh, I see what you're saying.
I know.
Oh, okay. Oh, yeah, you do. So you'll sit up here.
Well, I can't stand up here, but I
Okay, sounds good, thank you. Alright, so. This side slide down. This side slide down back. It's not really great. This flap. And that's the same way. So if you're looking at it from above.
Right? Like you get 4.0. But I know, like, I know what you're talking about. Yeah, I know. Yeah.
Oh, that makes sense.
Okay?
Yeah, thank you.
Okay, so I'll bring in the sheet after school. I'll ask the teacher on Friday if you want all of them for tomorrow. Or put it on a conversation. Okay, that's fine. I had a question on number 4, because I found that it wasn't continuous, and I'm not sure, like, when something was bubbling, and I wasn't sure, like, what I was supposed to show, I was just taking there, and I was
I'd say like 10 minutes.
It's like it's jamming stuff together and it's like, well,
I'm pretty sure it wasn't bubbling.
Except for about I saw this line, and I thought you were cutting this word out from the middle. I was like,
The function is,
or even make a box like and
that's
six
ribbon,
schools,
isn't
but
okay.
and then I'm gonna make them all, then I'm gonna make something, and then only like a 5. That don't think I'll
I can't put anything. It is continuous draw, real.
Last name is.
Leave the derivative.
You help me carry
We
something
can
else?
do that.
Okay. Yes. So you were 7.
It's in I know, they're all like.
You will get undefined. I think you'll get undefined
It's because we're not half an hour, half an hour after.
and an actual critical number of 0 and another.
The whole bag. Mr. Carlson. I made the
Oh,
box. He said mine was like,
it is
I
continuous,
end the box.
so it will.
Angie, what was the X that you got for your box?
Okay?
Was it like a check?
Yeah.
Okay, so that's, okay, that's right.
Fabulous.
Yes, I have a trigger.
Oh my God.
I know he does. The next question is,
Okay, now we
can
are.
you find this?
That's the wrong word to text?
This is a test. That's a test. Don't you wish your test looked like that?
Yeah.
Yeah, I did that after.
Yeah, what?
I made all the odd tests and questions.
What's yours done?
I have to sign.
All right, where we at? All right.
Mr. Carlson, remember when I got a finger in like 7 tests in a row?
I can't get that around the whole school.
Really? Can you put me on your wall? Can you put a picture of me on your wall and say I got 7 in a
Brooke
row?
Lucas, how about that? All right, Brooke, oh shoot, I forgot to pause this recording, darn it.